So we've always known how to find average rate of change. And new for us this year is this idea of letting the two ordered pairs that we're considering get closer and closer and closer together. In fact, take the limit as the distance between them goes to 0, and we can find instantaneous rate of change. How fast something is changing at an exact moment in time or at an exact value of the input variable. So that's what's new and exciting here is all this stuff that we've done to compute instantaneous velocity. This idea doesn't apply just to velocity. It applies to all kinds of functions. The input value doesn't have to represent time. So I present to you a tree trunk. The area, if you cut perpendicularly to how the tree is growing, we call that the cross section, right? The cross sectional area, which seems like I would compute by finding the area of a circle, it seems circular. That cross section area, it's getting bigger. And depending on what the radius of the tree is, it gets bigger at a different rate depending on how small the tree is when you cut it or how big the tree is when you cut it. So we can talk about the instantaneous rate of change of the area of this cross section of the tree trunk. So here we have an example. For a circle, we know the area is pi times r squared. Remember, pi is a constant. It's just some number, 3.14. So if I wanted to describe how fast the area of this tree trunk is changing as a function of the radius, I'm going to take the derivative, the instantaneous rate of change, the derivative. And here I can apply the power rule. So the 2, which is the exponent on the r, is going to come to the front to multiply the constant, the pi that was already there. And I have the derivative of the area with respect to the radius is 2 pi r. So this is the first time that we talked about the actual application of a derivative and didn't have, the input variable equal time. So dA dr, so the derivative of the area with respect to the radius. How fast is the area changing for a given radius? That's 2 times pi times the radius. So my next question, what is the rate of change of the area of the cross section of the tree trunk when the radius of the tree trunk is 4 feet? So it's another way to say, how fast is the area of the tree trunk cross section changing at the exact moment in time when the tree trunk's radius is 4 feet? So I want to show you this notation. I could have, instead of using this notation for the derivative, I could have just called my function a of r, and I would have said a prime of r is 2 pi r. That's totally equivalent to what I did before. It's just a different notation to say the same thing. So here, with this notation, it's a little easier to see that what I want is a of 4. Sorry, a prime of 4. The derivative of a evaluated when r equals 4. So we need a notation to say that same thing when I use the other form of derivative notation. So what we use is this tall bar, and I read that evaluated at. It's the same tall bar you saw when we practiced finding numerical derivatives on your calculator. So I would say dA dr evaluated at r equals 4 is 2 times pi times 4. That's this formula evaluated when r equals 4. So 2 times pi times 4, 8 pi. Again, that notation, dA dr evaluated at r equals 4 is going to be my dA dr formula with r replaced by 4. So 2 times pi times 4, 8 pi.